Alright, so we're reaching now at the master class video number 4. So, alright, so still in our master class video number 4, where the topic is the application on integration. So there will be now 3 topics to be discussed, such as the length of the curve, the surface area, and the centroids. So our objective is that we should know how to apply integration in these 3 topics. That would be in your length of the curve, your surface area, and your centroids. So, let's start with the length of the curve. So, with length of the curve, for the length of the curve, let's say I have here a curve which from limits of A to B, and this is your X and this is your Y. So for the length of the curve, we put here your strip. I don't know if you could see the strip, but I highlight the strip here. So for the length of the curve, that would be by using the Pythagorean theorem. So for the length of the curve, this would be the top part here. This would be your DL. This is the differential length. And for the sides here, this would be now your DY. With here, your DY, and your from the bottom here, this would be now your DX. And still, from the strip here, parallel to the x-axis would be your X, and this from your strip here parallel to your y-axis, that is your Y. So now, because we will be using your Pythagorean theorem, as you can see here, you could write this as DL is equals to your dx squared plus dy squared. This is a y. So, dl squared equals to dx squared plus dy squared over your dy squared also. So, if you now plot in that, this would be now your what you call this, this would be now all right. So sorry for the pause there. So this would be now, if you now distribute dy squared to each of these, this would be your dl squared over dy squared is equals to your dx squared over dy squared plus your dy squared over dy squared. So if this is equals to 1, and now for your, if you take it's a, what you call this, if you take this, it's a square root or or your square root, or because it's dx over dy, or I would not rather take its square root, but as you can see here, your dx over dy, this is your derivative or your prime x prime. So now, if this is your x prime here, this is your derivative. So if you take the square root of the dl squared over dy squared here, you take its square root. So when you take its square root, you could actually, this would be now your dl, and this is now your dy. So actually, you can take dy here and transfer it, or what you call this, you get its reciprocal. The reciprocal of 1 dy, 1 over dy would be dy if you transfer it. So if you now place it everything in its what you call this, in its, for the formula, this would be now your x prime, because dx squared over dy squared is your derivative, and that would be your x prime. So, and this is also your, it's b squared plus 1. And now if you take the derivative, rather the square root of the dy squared, and transfer it on the other side, this would be now your dy. And actually, because it's squared here, it still has, it's squared. When you take the derivative of this side, you also need to take the derivative of this side. And this would be now, the dl is equals to, this is your formula, your differential length is equals to the square root of x prime squared plus 1, or in the textbook, this is dl is equals to the square root of 1 plus x prime squared dy. And this is now actually, or rather, if you now take what you call this, if you take the integral of this side, and you take the derivative of the differential length, that would be now length is equals to the derivative of square root of 1 plus x prime squared what you call this, dy, with limits from a to b. And this is on dy, or on your x-axis. For now, for your y-axis, actually it's still the same when you derive this, because this will be now still your this is your formula for dy. And if you take it from your dx, this would be still dl squared over dx squared is equals to dy squared over dx squared plus dx squared over dx squared. It's the same as this. I'm just replace dy with dx. So if you take its derivative, if you as you can see here, the dy over dx, it's your derivative, and this is your y prime. And dx over dx squared over dx squared is equals to 1. And if you take the derivative of these two, this would be now dl y prime plus 1 square root. It's the same as in the, what you call this, in the other side here. So this dl is equals to square root of y prime plus 1. And because of the dx squared here, this would be now 1 over dx, or dl over dx. And you transfer, just like here, you transfer dx on the other side. And when you transfer 1 over dx, that would be dx. You take its reciprocal, and this is the differential length is equals to square root of y prime plus 1 dx. So if you take the integral of that, that would be now your this would be now your length is equals to the integral of square root of y prime plus 1 dx with limits from a to b. And actually, from the book, you could say that your length is equals to the integral of 1 plus y, or rather your y prime of y prime squared here dx with limits from A to B. Here also it has its squared, and alright, so that would be it for the formula in your in your x-axis and your y-axis. So you have these two formulas. So for the problem or the example, this would be now the length, for number 1, find the length of the curve with find the length of the curve of x plus y is equals to 25, or rather 5. No, x plus y is equals to 5 with limits from with limits from x is equals to 0 and your limits from x equals to 0 to let's say 5. So as you can see that x plus y is equals to 5, that is a circle. So we need take the quarter circle with limits from 0 to x is equals to 0 to x equals to 5. So now this would be your 0, and when you create your quarter circle, this would be now your y, and this would now be your x with limits from x is equals to 0. Alright, so as earlier as I said, in this could actually now be your because if you take out this dl dy over dx, if we put it here, this would be now your right your right triangle. This is now your dl, your dy, and your dx. So actually it connects from here. Your right triangle could apply in the Pythagorean theorem as earlier as I discussed. And so this is your dl, dy, and dx came from the right triangle, because when you find the length of the curve, it's by using Pythagorean theorem. Alright, so back in the problem, so we could create a strip here, and it's let's say I'm gonna make it bigger so you could see, and could strip here, and this is now your dl, this is your dy, and this is your dx. So from this point on here, x is parallel to your x-axis, that would be your x, and from point here parallel to your y-axis, that would be your y. So now if you take out the strip there, could say that this would be now the triangle here, that this is your dl, this is your dy, and this is your dx. Excuse me for that. And so we could now plot the formula that this is your dl is equals to the square root of because we're now taking it on the we're gonna do it from taking it from the y-axis in the x-axis. So in this one given, we're gonna make two answers, and we're gonna compare our answers with that. So now this is gonna be now your 1 plus because we're gonna compute it for using dx, or rather we're gonna use dx, so this will now be your y prime. So we're gonna use y prime. So for the for the length of, or rather from the quarter circle, this x plus y is equals to 5 here. We're gonna what you call this? We're gonna substitute it, or rather we're gonna make this gonna be a y. So you're just gonna transfer x on the other side. So that would be now y is equals to 5 negative of x. So this is now your y. So this is now your y. And don't forget actually the squared. So this is now your y. When you take your y prime, this is gonna be now is negative 1. So dl, if you take now the differential, what you call this differential length, if you take the derivative of that, integral rather, so the integral of dl is equals to the integral of square root of 1 plus your y prime is negative 1 squared dx, with limits from using x is equals to 0 and x is equals to 5. So when you take that, it would be now length is equals to the integral of square root of 1 plus the square root of, if you raise 1, negative 1, that would be now negative 1 times negative 1, that would be now positive 1. You take its derivative here. So this would be now actually from limit from 0 to 5. If you input that in your calculator, let me get my calculator. So when you calculate integral, don't forget to put your mode on radians. That would be now shift and mode, and you pick number 4, that is radians. So now this is the integral of integral sign, which square root of 1 plus 1 dx, with limits from 0 to 5, and your answer would be 7.07. And the units of this, or rather the units, it's units. And this is by computing now your length with dx. So now we're gonna, for number 2, gonna use this for your by using dy. So now as for this formula here, because x plus y is equals to 5, you could actually transfer now x is equals to 5 negative x, or rather negative y. This is would be your y. So now your x is equals to 5 negative y. So as per using this, or this illustration here, it's still the same by using the formula of the differential length, but we're gonna do it by, that would be dl is equals to square root of 1 plus the x is equals to 5 minus y. If you take the y prime of that, or the derivative of x, that would be now negative 1. It's the same because we're using a circle, or we're gonna take the quarter circle of this, so the answer would be actually needed to be the same. So this would be now 1 plus of x, or x prime squared dy. So as we what you call this, this is now your dy. When you take the integral of the differential length, this will be now length, the integral of 1 plus your what you call this, your x prime, x is equals to 5 minus y. This, your x prime is negative 1. This would be now your 1 negative squared dy. It's the same as here in the top. So, and don't forget the limits. The limits of this, because only in the x-axis, and still because this is a circle. The circle has the same the same radius and all. So this also would be the limits would also be 5. So it starts from 0 also to 5. Now, L, or your length, is if we now take the integral of this would be still as the same answer, because if you take the integral of this would be 1 plus positive 1 squared dy. It's the same answer on by using your, or computing for your using dx. And still, this is also negative 0.07 units on dy. So, this is an example for your surface, or rather the length of the curve. So, first, don't always forget on how to, what you call this, to formulate your what you call this, your formula, because from the length of the curve to the surface area to the centroids, in every step, in every topic, we will gonna use that on the centroids. So this is for your length of the curve. So you could take a screenshot of it, or take a picture of it, so you could actually copy it first. And this is also your y. Sorry for my bad writing. I don't have any whiteouts anymore because of I'm lacking of whiteouts. So this is for the length of the curve. For the next topic, this would be now for your surface area. So let me get my what you call this, my another paper for the surface area. Alright, so for our next video, or for the next topic, is the application of integration in surface areas. So let me first derive or explain how the surface area formulas, or rather derived. So if you now, as you can see here, if I have this the plane, which this is your y and this is your x. If I have here my curve with limits from a to b, you could put here your strip. This would be now, as before, as I discussed before, this is now your dl, because from the length of the curve, the what you call this, the lessons, or rather the topics, is connected. So we still need to take, or rather when the derivation of the formula is still alike, but it's still from the length of the curve. So this is now your dl, your dy, and your dx. If we put out here, this would be now your dl, dy, and dx. Alright, so if we take up, this is now your dl, your dy, and your dx. If we now put here, this is would be now your strip. If we now put, this would be now your surface area here, because we're computing for the surface area. And this is like gonna be like this, the big one and small one. So we're what you call this, this would be now the surface area. So if we take out this here, and actually don't forget length that is parallel to your y-axis is your y, and still from your point here, from your strip, this is your x. And now bakit? So if we're gonna take the strip out, this would be now your strip, and your axis of rotation is on your x-axis. This is your AOR. So this is now your strip. From the strip here, from your axis of rotation to the point here, this is now your y. It's still the same as I discussed in my previous master videos. It's still the same because the derivation of the formulas is connected to each other. So if you want to learn the surface area first, you need to learn back before my topics on this, and that would be on the length of the curve, or rather from the first lecture video, or rather from the first master video, is from the area. So back here, so this is now your y, and this is your differential length. This part here is your differential length, and if you now, what you call this, if you now half or get the half of this would be also your strip, or the circumference of this. So that would be now your 2 pi y, because your y, you're using your y. If you cut it in half, the circumference, or rather the what you call this, the circumference, that would be your dl. Your strip here, this would be your dl. And so when you now plot your formula, this would be now your differential area, or rather and this is now from your strip here, this is now your differential of surface area. So differential of surface area, if you have here your 2 pi y, this is your 2 pi y, and if you remember, you have your strip here, this is your dl. If you remember from the previous video, or from the previous topic rather, your dl, your dl actually is equals to your what you call this, your dl is equals to your 1 plus x prime of squared dy, or actually this also is dl is equals to 1 plus y prime squared dx. So if you remember this from the previous video by the length of the curve, you will now apply also in the surface area. So this would be now differential of the surface area is equals to 2 pi y square root 1. Let's use the if you have y here, because we're on the x-axis, we need to use your dy, or your dx, because we're on the x-axis. Our rotation is on the x-axis, so we're gonna use dx. This is on your y-axis of rotation, on your y-axis. So this is on your x-axis. So we're using that in this derivation of formula. So this would be now square root of 1 plus your y prime squared dx. And so if you now get the integration of the differential area, and also here, this would be now, let me divide this first, this would be now the integral, rather now the what you call this, it's not, so this would be now the surface area of the integral of 2 pi y, let's say this would be now dl, or rather let's use the because we're in the y, or rather in the x-axis, we're gonna use your dx, or so this would be now the integral of 1 plus y prime squared dx with limits from a to b. Actually, if you're now if you're now on your y prime or y prime, no, your y axis, actually you could actually change this. Your dl, you could use the square root of 1 plus x prime squared dy, and this is only actually your two formulas by using your dl, because this is only will vary on your where is your axis of rotation, whether that would be on your y axis and your x-axis. Alright, so for the example for the surface area would be now, if we have here, find the surface area of the curve that let's say, find the surface area of the curve y is equals to x squared, with limits, let's say your limits would be from 2 to 4 and rotated on the x axis. And so if we plot this now, this would be now your y, and this is now be your x. And so as you have known, or as you from my previous video, that x squared is a parabola which originates at 0, 0. So this is now your curve, and let's say this would be 2 and this would be 4, and this is your limits. So this is your curve. So now if we could plot in your strip here, I hope you can see. This would be now your strip. This is the right triangle. This is your DL, and this is your DY, and this is your DX. So from this point here, this is your X because it's parallel on your X axis, and this is in your Y because it's parallel to your Y axis. So now if you plot in the surface area, this would be, and this will be serving your this is the strip here. Your strip would be now your dx, or your dl. So if we put this outside here, if we copy your strip, so this is on your strip here, this would be your dl, and because your axis of rotation is on your x-axis, and from this point here, from the illustration, from that point here, this would be your y. And actually now, from the inside here, this is now your differential area. But if we cut it in half actually, and we take the strip here, your differential length, this would be now your dl. Your dl here, your dl, if we cut it in half, the circumference of that would be your 2 pi y. So we could now plot in your differential surface area. So this would be differential surface area is equals to 2 pi y. As you have known, your DL, as we discussed it on your previous topics, on length of the curve, that DL is equals to 1 plus y prime dy, or rather dx. Or also, that would be DL is equals to 1 square root of 1 plus x prime squared dy. Don't forget, because as I said earlier, that your topics is connected to each other until you reach centroids. So this is from the length of the curve from the previous topic. So this would be your DL. So if you integrate this would be now the surface area is equals to 2 pi y because we're on the x-axis or the axis of rotation on x, we have to use your different dx. So this would be square root of 1 plus y prime squared dx, in which we have from limits from 2 to 4. So now if we substitute your y, that would be your x squared. This is now the integral of 2 pi x squared, the square root from 1 plus your x, or rather your y, your y is equals to x squared. So your y prime is actually just taking the derivative of the x squared, that would be 2y. So this would be now square root 1 plus 2y, or rather 2x, not 2y, 2x squared dx. And so from this point on, you could now actually input this in your calculator. So the surface area, and don't forget the limits, silly. So this would be now the integral of 2 pi x squared square root from 1 plus 2x squared dx with limits from 2 to 4. So now we could now get to integral. So this would be 2 pi multiplied by x squared with square root from 1 plus 2x squared dx with limits from 2 to 4. So for your answer, that would be 763, 300,000 chuchu, or so on and so forth. That would be 763.34 squared units. And this is for your number 1. Alright, let's have another problem. So let me get a new piece of paper. For number 2, so let's say now, for number 2, let's say you have now your curve at x is equals to square root of y, with limits from y is equals to 0 to y is equals to 5, and rotated on your y-axis. With this now given, you could now actually plot this. This is your y and this is your x. As you know, or rather as we what you call this, from my previous video, we plot square root of y many times. So if you want to know that, you could actually watch my previous videos, or you'll actually plot this on GeoGebra, or you could use your tabular method. So but we're gonna focus on, that is from my previous video, so but we are gonna focus on your surface area, so we're gonna shortcut that. So this is now your what you call this, your x, and that would be the square root of y. So we have limits from 0. Let's say this will be now your 5, and we could now plot your differential area, or rather differential length. So we could put now your strip here. When you put your strip here, this is your DL now, and this is your dy, and this is your dx. From the point here on your strip, in which parallel to your x-axis, that would be your y, and from this point of your strip parallel to your y-axis, that is your y. Rather, from this point here, let me do it again. From this point here, your strip parallel to your x-axis here is your x, and from this point here, from your strip going downwards parallel to your y, that is your parallel to your y-axis, that is your y. So now, because from the from the from the given x is equals to square root of y, that would be now we're gonna do it on your y axis. So when you plot your strip, it's going to rotate on your y axis here, and this is now your strip. So if you put your strip here, if you write this again, this is now your DL. And from this axis of your rotation, from the point here, because this is your axis of rotation now, from this point here, your DL, and in which parallel to your y-axis here, this is your x, not parallel actually, but you cannot, but is parallel on your y, or rather your x-axis. So this is your x, and we could, if we could now cut that in half, we take the circumference of that, the strip here, the circumference of the strip. We could now put that as that formula would be now 2 pi of x, because we have x here, and this is your DL, and inside here is the surface area, or the differential of surface area. And so if we could plot now your formula, this would be now this differential of surface area is equals to 2 pi of x dl. As I said earlier, from number 1, your dl actually has 2. So we're gonna use the other now. So that would be on parallel, or rather on the axis of rotation on y. So this would now differential area is equals to 2 pi of x square root of 1 plus what you call this, x prime squared dx. So this now your halfway in your formula. So if we could take the integral of the differential surface area, this will now the surface area integral of 2 pi of your x is square root of y square root of 1 plus your, what you call this, your, because your x is square root of y, and you take the differential or the derivative of your x, that would be now prime y, is equals to 1 over 2 square root of y. That's because if we could do this as y is raised to 1/2, if you take the derivative of that, would be now 1/2 y raised to negative 1/2. So we're gonna put your y to your denominator. That would be now 1 2 square root of y. So this is your y prime. That would be now 1 over 2 square root of y squared dx. So now from this point here, and actually don't forget the limit, in which from 0 to 5. So from this point on here, you could now actually input that in your calculator. So the integral of 2 pi square root of y, because it's the, what you call this, the calculator is programmed that's only for dx. So we will pretend that y is x here. So this will now square root of x multiplied by square root of 1 plus your dl, or rather your 1, or your y, your x prime. So that would be now 1 over 2 square root of y, or rather your x squared, with limits from 0 to 5. And because this is gonna be a math error, from the previous topics of my professor, because it's gonna be a math error because it has square root and this is a 0. So if we could use that, if we're gonna use 0.001, the limits from 0.001 to 5 to pi square root of y, integral of 1 plus 1 over 2 square root of y squared dx. This actually occurs of one of the examples of my professor to me when he taught us the surface area. So actually do that, instead of 0, he put that 0.001. So the answer is 49 is surface area is equals to 49.86 squared units. So this is your final answer. And please take note that sometimes, because your answer here will be gonna math error because of the given, such as because we are using square root of y, and this will gonna be a math error, so you will be reaching infinity or undefined. So this is now using, instead of 0, you could actually put 0.001 to have a limit. So the answer is 49.86 squared units. And that is for your surface area sample problem number 2. So next, now for your centroids, let me get a piece of paper again. Alright, so we're gonna compute, or rather we're gonna solve now for centroids. Centroids is our next topic. So centroids. So for centroids, let's say I have here a curve which has limits from A to B, and you now put here your strip. But first, before I forget, so actually centroids are is also taught you, or is also taught in physics, you know. So for now, I'll just assume that you know centroids way back on your physics class, because this is now calculus, so we're gonna focus on applying integration on centroids. So I'll just skip to that process, and we're gonna go right through, or we're gonna go directly to computing on centroids by integration. So first here, we have a strip, or what you call this, or rather we have a curve in which from A to B, in which has a strip here, and this point here is your centroid. So this point here, if going down or parallel to your y, this point here, this is your centroid. So this would be now your YC, and that YC is equals to y over 2, and let's say this would be your YC. In your physics, that would be your y bar, and in this, let's say this is your XC or YC. So from your centroid here to the from this length, this would be now your XC, or your X is also equals to X here. So this is now also your X. So now, and from this point on here, from the top of your strip, that would be now your Y. And this because your XC here, we're only computing its centroid here. But for your Y here and for your X, we're computing the area. So now you should not be confused because your XC is only for your centroid, and your for Y here is for your area, the area of the centroid. And don't forget that still the same. This is your dx, the thickness, the thickness. If we put out your centroid here, this would be still that is your x, or rather your y, and you have your point here, your centroid. This would be your yc, which is equals to yc is equals to y over 2, and this is your dx. On centroids, don't also forget your differential area. On centroids now, your differential area is still the same from my previous videos that I've been teaching you, that differential area is only equals to y dx. So, if we could now integrate this would be now your a is equals to integral of y dx, in which it has from limits from a to b. For your formula in your previous from your physics now, your yc is equals to your area, from your area multiplied by yc, your yc here, over your area total, or your a tot. So this would be now what you call this, your area now here, your area is equals to y dx, and for your yc here, that is your y over 2 over a tot also is y dx with limits from a to b, and also here y dx, don't forget that it has limits also from a to b. And this is for your yc, but could also rewrite this as your 1/2 y squared dx. Could also rewrite this as this 1/2 y squared dx. And for your xc, let's say your xc now, and also don't forget that your yc also is equals to your y bar. Your y bar is equals to yc, and yc is equals to area y multiplied by yc over area total. So now for your xc, this is also area xc over a total. For your a total, that would be now the limits from a to b, in which, because your xc also here, your xc is equals to x, such as this would be now x y dx over integral of y dx area a to b. And this is mainly your two important formulas, your xc and your yc. So let's get another paper for your example. For example, in centroids here, let's find the centroid of a curve y is equals to 2 cosine x with limits from x is equals to 0 to x is equals to 2. So now when you plot this, from my previous video, I already taught you on how to plot your curves. So I already plot my curve that y is equals to 2 cos, y equals to 2 cosine x. This would be from this 2, and from this point on 2 here, your 2 cosine x will be straight, form a line with limits from 0. So this is your line 2 cosine line. Y rather, y cosine 2 cosine x. And so now we could create here your strip in which it has the centroid in the center. This would be your yc is equals to y over 2. This is your xc, the centroid. From your centroid rather, xc is equals to x. And from this point here, from your horizontal, your vertical strip, this would be your x. The thickness would be the same as your dx. And from the point from where your strip began, this would be your y. As I said earlier, for your centroid is only you're computing for the centroid. And for your y and your bar x and your bar y, rather, sometimes you could say that, so this you're computing for the area of the centroid. So now, if you take out your strip here, this would be now, from your centroid here, this is your yc is equals to y over 2. And from your xc, here, you could say that you have your xc, and this is now your y. You cannot actually put your xc. I forgot because we're on using is vertical strip in which parallel to your y-axis. And so for this formula here now, by this strip rather, don't forget the strip, that strip is the differential area. This strip here is differential area is equals to y dx. If you integrate this would be now your a, integral of y dx a to b. So do you remember this? This is from my previous video, from my first master video or second master video. I already taught this on areas. So from earlier, as I said, on computing on your centroid, that let's put it here, that yc is also equals to your y bar is also equals to your area multiplied by yc over area total. And you could say your area here is the integral of a to b y dx. And your yc, from earlier here, your yc is equals to y over 2. And if you could rewrite this would be 1/2 of y squared dx. And so, over the area total, so your area total is actually only your integral of a to b y dx. And now, if you substitute your y, your 2 cosine x, rather, your 2 cosine x there, this would be now the integral of 1/2 2 cosine x squared dx over with limits from 0 to 2. Don't forget the limits from 0 to 2. So the integral of your y, 2 cosine x dx with limits from 0 to 2. And you could actually now input this in your calculator. So when I put that in my calculator, this would be now, let's first put the divide or the fraction. Let's first input the numerator here. This would be now 1/2 multiplied by 2 cosine x squared with limits from 0 to 2 over also the integral of 2 cosine x with limits from 0 to 2. And for your YC is 0.891. This is for your YC. And now, for computing your XC, basing on the formula on your XC is area total, or rather area XC over area total. So, for your area is still the same, in which that is the integral of y dx with limits from a to b. So, let's say it's from y dx with limits, we're gonna use our limits from 0 to 2. And your y, or rather your xc here is only equals to x. This would be now your x multiplied to x of, or your area total. Your area total is still the same, in which that integral of y dx with limits from 0 to 2. So now, this would be, if you rewrite this would be now your x, the integral of x, your y dx here. Your y dx is 2 cosine of x dx with limits from 0 to 2 over area total, in which is only 2 cosine x dx with limit from 0 to 2. And so we could actually now just rearrange this. We would take out the 1/2 here. So actually now we could rewrite just this. We could just get the squared here, and we could just get the squared and put an additional x and take out 1/2. So this is still the same, in which the integral of 2 cosine x multiplied by x dx with limits from 0 to 2 over integral of 2 cosine x dx with limits from 0 to 2, and this is for your xc. For your xc, that would be now for your xc is 0.442. And don't forget the units. You could say that they don't have actually the same answer, or rather because it's not, because for your xc and your yc, you're only computing for the centroid here. And for your y bar, you're computing for the area of the centroid. So for your y bar, actually this would be now is equals to 0.4442 units. And for your y, this would be now 0.891. And that's all for centroids. So thank you for watching all the way to my master class video number 4. And so, I hope you learned something, and thank you for watching. Like, comment, and share, and subscribe to my channel. Alright, so, and have a good day.